Hello guys, how's it going? Today we're gonna continue with the fourth course on this Associate AI Engineer for Developers. I'm just gonna check that the stream is good and that the audio course, yeah, that's good. And well, yesterday we finished with the Hugging phase. It was pretty nice. It shows how to use open source models that we can probably host in our own servers or from some provider. And now we're gonna go today with the LLMOps concepts. So let's just jump right into it and see what this course has to offer.
Welcome to this conceptual course on large language model operations, or LLMOps. I am Max Kowout, and I work as an applied scientist at Uber, focusing on researching and developing AI and machine learning solutions. LLMOps involves the specialized practices, processes, and infrastructure required to effectively manage, deploy, and maintain large language model applications throughout their lifecycle. This is important for any organization wanting to use LLMs effectively. This course covers the fundamentals of LLMOps, its lifecycle phases, and addresses associated challenges and considerations. Let's revisit the fundamentals of LLMs to understand the need for LLMOps. These models are trained on extensive text data, enabling them to understand and generate human-like text. They mark a significant breakthrough in AI technology. LLMs differ from traditional machine learning models by being pre-trained on vast data sets, having a massive number of parameters, requiring significant computational resources, sometimes exhibiting unpredictable behavior. When LLMs were first introduced within organizations, the process was simple. Queries were directly fed to the model to generate output. The focus was on operating the model, with little considerations for providing it with new data. Only when the model was fine-tuned did organizations need to introduce their data. Today, we recognize that maximizing the potential of LLMs means providing the right data at the right time. For example, integrating organizational data before text generation is common practice, involving multiple tasks such as data processing and manipulation. These steps can include one or multiple model calls, accommodating different types of inputs, such as text, image, or multimodal. These LLMs are integrated into the organization's ecosystem, seamlessly incorporating its data, resulting in what we call LLM applications throughout this course. LLMOps ensures the seamless integration of these LLMs into the organization, aligning them with existing processes. Moreover, LLMOps ensures a smooth transition across lifecycle phases, from ideation, development, to deployment. Additionally, LLMOps provides efficient, scalable, and risk-controlled management of LLM applications, enabling organizations to maximize benefits while minimizing risks. Therefore, LLMOps is essential for effective LLM use. MLOps involves managing the operational aspect of machine learning models, while LLMOps specializes in handling the unique challenges posed by LLMs. Both share similarities, but also differ. Let's compare. LLMOps deals with large-scale models, whereas MLOps typically handles smaller models. LLMOps primarily focuses on text data, while MLOps focuses on any data. LLMOps often leverages pre-trained models, whereas MLOps typically does not. LLMOps involves techniques like prompt engineering and fine-tuning to enhance model performance, whereas MLOps employs feature engineering and model selection for improvement. LLMs are general-purpose models capable of handling a wide range of tasks and domains, while ML models typically focus on models with fixed scope, tailored to specific tasks. Due to their size and complexity, LLMs are more unpredictable and may even generate incorrect information, called hallucinations. In contrast, traditional ML models are generally more predictable. LLMs primarily produce text as output, while ML models generate task-specific outputs, such as labels or probabilities. While LLMOps and MLOps share similarities, they diverge in their focus, methodologies, and the types of models they handle. As the demand for LLM applications rises, the importance of LLMOps becomes increasingly evident. Now let's put these learnings into practice.
Nice. So to understand how to use LLM effectively in organizations, you need to look at the unique challenge of LLMOps deal. So using model architecture tailored to specific data characteristics. The specific data characteristics and task, I think this is MLOps. If it's too specific, dealing with lightweight task is okay. This is for specific data characteristics and task, and dealing with lightweight task, like really small, it should be MLOps. General purpose handling aware task and domains is more general purpose. There's some profiling and fine tuning is here. Models with high predictability due to the size and complexity. This. So if it's specifically tailored, it should be here, I think. That's correct. Relevancy of LLM ops. Why is LLM ops essential for organization? To manage the text data effectively. to ensure seamless integration of LLMs into organization.
Now that we understand the importance of LLMOps, let's explore the topic further. In this video, we will provide an overview of the various stages and life cycle of LLM applications. In Chapter 1, we'll delve into the ideation phase, which is about planning. In Chapter 2, we'll explore the development phase, focusing on building the application. Finally, in Chapter 3, we'll examine the operational phase, which is about deploying and maintaining the application. We have the ability to shift between different phases, moving in both directions as necessary. The arrows connecting these phases signify the flexibility of the process, which doesn't always follow a sequential path. For example, during development, there might be additional planning, leading us back to the ideation phase. Likewise, in the operational phase, we might identify the requirement for further application development, motivating a return to the development phase. This course aims to provide a conceptual understanding of these phases and how they relate to each other. The first step of the ideation phase is data sourcing, which is the process of identifying data needs, finding data sources, and making them available. We then move on to base model selection, which is about selecting the right base LLM for our application's use case. In the development phase, we start with prompt engineering, where we focus on crafting effective prompts to ensure the model produces accurate outputs. We should think about different architectures for shaping our application, such as chains and agents. Various techniques exist that boost the model's performance, such as RAG and fine-tuning. The last consideration in the development phase is testing, which is about determining when the application is ready for production. In the operational phase, our first activity centers around deploying our application to production. Moreover, monitoring and observability helps us keep track of how well everything is working. Another consideration is cost management, which is about handling the expenses associated with using these models. Concluding the operational phase is the implementation of governance and security, which includes access controls and measures to mitigate threats. Understanding the specific phases helps us prioritize activities, allocate resources effectively, set realistic timelines, and identify potential bottlenecks. Putting all of the pieces together gives us a full picture of the LLMOps lifecycle. This overview will act as a guide throughout the chapters. With a good grasp of the lifecycle phases and their activities, let's apply this knowledge in practice.
Okay. The purpose of a life cycle phases. Which of the following steps explain the significance of knowing different phases of LLOps, so select the two answers to apply. So determine life cycle phase aids in resource allocation and planning, yeah. It's false. Knowing the current life cycle phase help us make decisions positively. Not consider phases. Accurately, I don't think so, because there's variation. Application lifecycle. Each step in an LLM lifecycle includes key activities. Knowing what needs to be done each stage, highlight which each phase is essential, and show how the application matures as it progresses. All right. So prompt engineering, it's in the development phase. Testing that the application works as intended is in operational phase. Which is ideation phase as a base model. The cost management is in the operational phase. Performance monitoring is in the operational phase. And yeah, testing the application. Okay, it can be done in both actually. So
let's explore the initial ideation phase of LLM application development. During the ideation phase, we dive into understanding the business problem through data sourcing and base model selection, ensuring the right scope and requirements for successful development in operational phases. Providing the latest data is essential when developing our LLM application. This data serves as the fuel that powers the reasoning capabilities of the model. Data sourcing involves identifying needs, finding sources, and ensuring accessibility of the data we want to use. 3 questions will guide us. Our first question is the data relevant? This involves identifying the right information from internal or external sources. Our second question is the data available? Sometimes we need to transform the data to make it ready. Additional databases might be needed for text data searchability. Evaluating costs, particularly for external data, is crucial as accessing it may incur charges. Finally, consider access limitations related to volume or frequency. The last question is, does the data meet standards? These standards may concern quality and governance. If the data contains confidential or sensitive information, it could impact the choice of base model, since we might need to guarantee that it remains within the organization. After identifying data sources, the next step is selecting the base model. Most organizations choose pre-trained models, which already have been trained on a significant amount of text data. The first step is determining whether to use a proprietary or an open source model. Proprietary models, such as the ones shown here, are privately owned, while open source ones are publicly accessible. Crucial consideration is whether exposing data to a third party is acceptable, since proprietary models cannot be hosted within the confines of the organization. Some advantages of proprietary options are ease of setup and use, quality assurance, and guarantees on reliability, speed, and availability. It requires us to expose our data and offer limited customization. Open source options offer advantages such as in-house hosting, transparency, and full customizability. However, they offer limited support and do not always allow commercial use. Moreover, customizing these models requires dedicated AI engineers. These models can be downloaded from online model hubs. After deciding between proprietary and open source models, we need to narrow down our choice to reach our final selection. This means evaluating factors in 4 categories: performance, model characteristics, practical considerations, and less important secondary factors. For performance, we should consider the response quality, often better with the latest released models, and speed, crucial for real-time applications. For model characteristics, consider the data that was used to train the model, ranging from web pages to code bases, affecting the responses we might expect. The context window size refers to the number of words a model uses to predict the next word, influencing quality. Finally, fine-tunability allows developers to optionally adjust the model for better performance. For practical considerations, consider the type of license associated with the model, especially relevant for open source models with commercial restrictions. The cost and the environmental impact should also be considered. Finally, there are less important secondary factors like number of parameters and popularity. These are often indicators for quality, speed, cost, and power usage. With data and base models set, we move to development. But first, let's practice.
Okay. Choosing the right data source is key as you start developing your LLM application. What application should be prioritized to guarantee the optimal selection of data sources for your application? What considerations should you prioritize to guarantee? The relevance, availability, and the quality of the data. That's it. Suppose your organization wanted to develop an LLM application. Your task is to decide between opting for a proprietary-based model or utilizing an open source with on-premise hosting. Classify each use case into the rate. So the chatbot taking into account your personal data. I think I'll use open source because then I can have I with the proprietary that doesn't we are exposing the data. I'm just summarizing medical records for use by medical staff. For the product, you can use a proprietary. You don't need to have too much control over the data here. You can use a proprietary. Architecture can use an open source. Identify the primary factors to consider when selecting a base model. Response speed, license type, model popularity, and also the cost. I mean the CPU processing cost. Number of parameters of the model is not. Well, yeah. Although you mentioned that in in the lesson, which is really funny.
We are now ready to start the development phase. The first task is to load the base model selected in the ideation phase and start prompt engineering. The development phase is a cyclic process of building and improving the application, known as the development cycle. At the heart of every application is the prompt, which instructs the LLM to generate the desired outputs. We'll revisit this cycle as we progress, filling in new parts as we learn them. But why do we care about prompt engineering? Prompt engineering enhances prompts in 3 ways. By giving clear instructions, we can improve performance by getting more accurate and helpful responses from LLMs. With well-crafted prompts, we gain more control over the output, steering LLMs to generate the desired content. These models can make mistakes or produce irrelevant information. Prompt engineering helps us avoid bias and hallucinations. But how do we find the perfect prompt? A typical prompt includes 4 elements: an instruction for the model, examples or additional context, input data, and an output indicator. In our example, we want to predict calories of a dish. Instructions specify the task and format, examples are other dishes' calories, input is the actual dish, and the output indicator guides what the model should produce. When testing prompts, it's worth adjusting LLM settings, such as temperature, affecting the randomness, or max tokens, affecting the output length. Additionally, we can enhance prompts by using in-context learning, where we show the model examples of inputs and outputs. Numerous online resources offer prompt design patterns to assist us. A playground environment is useful for trying various models and settings. Each prompt acts like a mini experiment. At this stage, we're evaluating prompt quality using our own judgment. When finding that perfect prompt, tracking results, known as prompt management, is crucial for efficiency, reproducibility, and collaboration. we should track the prompt itself, its output, along with details about the model and settings used. This way, we can revisit and reuse past results. Using a dedicated prompt management tool or a preferred version control system is recommended. At this stage, we should begin generating a collection of good input-output pairs that can be used to evaluate the application later on. Once we've gathered a collection of promising prompts, we're ready to proceed. We can always return to...
This is something interesting because normally in code you have like the Git control version, but I am not sure about the prompt manager versioning. I assume that will be the same as we'll be using still Git, but maybe not. I don't know.
Define our prompt engineering later on. Right now, it's crucial to start developing prompt templates. In our application, we have input data that we need to transform to output. These templates use placeholders for input and work like recipes for different tasks, fitting any kind of data. They're essential for making reusable prompts, making our application more flexible and efficient. For example, with our dish calorie prediction template, we can predict calories for any type of dish. This will be even more helpful as we create advanced applications. Starting from the original development cycle diagram, we are now ready to extend it. We add activity of prompt engineering to it. We use a dashed arrow to denote that this leads to new and improved prompts to be used in the LLM application. We've introduced the fundamentals of prompt engineering as we develop our application. Now, let's apply this knowledge in practice.
All right. The importance of so in this just in case in this chapter we're not gonna code, we're gonna learn full concepts, I assume so. So it's good. And then I'm gonna do something, gonna grab a haircut, and then in the afternoon we can start with the project, I think. Prompt engineering plays crucial role in maximizing the effectiveness of an LLM application. Can you identify some reasons why? By giving clear instruction, we can get more accurate and helpful response from LLMs. That's correct. That's not correct. Prompt engineering aims to completely eliminate randomness from the output. No, because it doesn't completely eliminate randomness. With well-crafted prompts, we can see the models generate the kind of content that we want. That's correct. Prompt engineering helps decrease bias and hallucinations of the output. Yeah, that's correct. Trying out prompt engineering. Prompt engineering is vital for optimizing the efficiency of LLM applications. Even slight variations in the prompt can greatly impact the output. Your job is to develop an LLM application to predict whether a food item will be popular. Choose which prompt will you prefer for your application. Prompt 1. Determine whether a dish will be popular or not. Give output as yes, no. Examples are bigger. This is a more clear one. Providing examples and clear output instructions. Keeping track of prompts. When finding the perfect prompt, it's important to keep track of your progress and results. A process known as prompt management. Why do you want to track prompts when working on prompt engineering? Help ensure efficiency, reproducibility, and collaboration within a project. Yeah, that's correct.
We are ready to make more advanced applications using chains and agents. While prompts are central to any application, chains and agents provide its flow and structure. Let's go back to our calorie prediction template. It requires examples and an input, which is the dish description. But how do we find examples? Suppose we have a database of dishes. We need to find similar dishes based on the description. Also, the application's output should be converted to a number for calorie calculation. To achieve this, we'll go through a few steps: receiving input, searching examples, prompt creation, output retrieval, and output parsing. We can use chains or agents to build this functionality. Let's start with a chain. A chain, also known as a pipeline or a flow, consists of connected steps that take inputs and produce outputs. For our example, we start with a dish description. First, we find similar dishes in the database. Next, we combine the dish description and examples with the prompt template. This prompt is then given to the LLM. From the output, we extract a number. This process demonstrates a chain in action. Chains are crucial because they enable us to develop sophisticated applications that interface with our own systems, establish a modular design, enhancing scalability and operational efficiency as our system grows, unlock endless possibilities for customization. But what if we need even more flexibility? Say our dish calorie prediction isn't giving optimal results, likely due to insufficient details like ingredients and quantities. Suppose we have the option to look up more information about a dish. We now have two actions: searching for extra examples or retrieving additional dish information. This is where agents shine. LLM-powered agents follow a design where actions, also known as tools, are available, and the LLM decides which action to take. An action functions as a standalone chain that generates output. Unlike deterministic chains, agents are adaptive. They can help us in scenarios with many actions, where the optimal sequence of steps is unknown. especially when we're uncertain about the inputs we'll receive. We're now faced with two actions: fetching more dish information or finding more related dishes. To decide, we give the LLM a set of actions and ask it to choose the best one. So, for example, we use an agent. Notice the backward arrows, indicating that these actions provide additional information. This also means each action can happen any number of times, and we don't know in advance how often. This complexity makes agents very powerful. Deciding between an agent architecture and a simpler chain is vital, as agents can be unpredictable. Let's understand their differences. Chains are deterministic, while agents adaptively choose actions. Chains are simpler, while agents exhibit more complex behavior due to their adaptability. Chains are less flexible, while agents can adjust to diverse inputs. Chains are less risky due to predictability, whereas agents might execute unpredictable actions, resulting in unpredictable outcomes. Let's return to the development cycle. Chains and agents enrich our application by enabling intricate sequencing, transformations, inputs and outputs, thereby enhancing our functionality. The act of creating chains and agents is called chain and agent development. Let's review differences between chains and agents.
Okay, just in case, just to make a small
Example,
and a small review here. When you have an agent, like you, for example, if you put a prompt text and it goes into the agent template, it goes into the prompt, then into the LLM. Depending on this output here, I'm gonna perform many actions that can call again the agent template past the prompt, and it's gonna be in this cycle until the system detects that I got the appropriate response, and then I'm gonna generate the output. So this is the agents generate cycles, and that's why, because the LLM by its own already has variability, adding cycles it adds more variability to the process, just in case. Change in engines is the key. So when we develop application, we need to decide if we want to develop a change, an agent, or both, or all mixed. So the agent is adaptive, yeah. The change is deterministic. Just for all single sequence of steps is unknown is with the adaptive. Low risk due to predictability is the chain. The LLM decide what action to take. Here's the agent. Picture yourself choosing between building an application using a change or an agent architecture. With both seeming possible, what decision would you lean towards and what factors would you consider when picking the right architecture? It depends. Since choice between an agent and check is about the balance trade-offs related to complexity, flexibility, and risk. Okay.
During development, we often need to incorporate proprietary data and external knowledge. Let's compare two methodologies: retrieval augmented generation, or RAG, and fine-tuning. RAG is a common LLM design pattern, combining the model's reasoning abilities with external factual knowledge. RAG consists of 3 steps in a chain: retrieve related documents, augment the prompt with these documents, and generate the output. This allows the LLM to use external data for better results. The retrieve step is crucial, as dealing with large knowledge bases can be challenging. Thankfully, there are ready-made solutions, often implemented using vector databases. Let's create a RAG chain with vector databases. First, we convert the input into a numerical representation called an embedding, which captures its meaning. Similar meanings yield similar embeddings. Embeddings are created using pre-trained models. Next, we search a vector database containing all embeddings. We compare the input embedding with those of the documents and calculate their similarity. Finally, we retrieve the most similar documents. The augment step combines the input with these documents to create the final prompt. The generate step uses this prompt to create an output. When implementing RAG, we face several implementation choices, especially regarding the embedding model. Open source and proprietary options vary in quality, cost, and ease of use. Certain models work well with particular text or languages, not others, making experimentation and testing crucial. Let's now explore fine-tuning as another method to incorporate external information. Unlike RAG, which incorporates factual knowledge, fine-tuning adjusts the LLM's weights using our own data. This process expands the model's reasoning capabilities to specific tasks and new domains, such as different languages or specialized fields. There are 2 main approaches to fine-tuning, each requiring different types of data. Supervised fine-tuning, a form of transfer learning, needs demonstration data containing input prompts and desired outputs. This approach retrains parts of the model using this new data. The second approach is reinforcement learning from human feedback, typically done after supervised fine-tuning. This requires human-labeled data, such as rankings or quality scores obtained from likes and dislikes. We then train an extra reward model to predict output quality and optimize the original LLM to maximize this. Both approaches require decision making and can be complex. So, when should we use RAG or fine-tuning? RAG is used to include factual knowledge. It retains all capabilities of the original LLM without altering it. It's easy to implement and keeps the application up to date if the external database is current. However, it adds extra components to the application, requiring careful engineering. When specializing in a new domain, fine-tuning is used, as it offers full customizability of the model without needing additional components during deployment. Yet, it needs labeled data and specialized knowledge to implement. Depending on the training data used, it may worsen the application and amplify data biases. It can even cause the model to forget previously learned knowledge, known as catastrophic forgetting. Let's return to the development cycle. With the addition of external databases, we utilize RAG to use this data in our application. The activity of fine-tuning allows us to tailor the LLM to new domains. Let's review RAG and fine-tuning.
Got it. The RAG workflow can be used to enhance your application ability to efficiently retrieve and generate relevant and coherent responses. For this, you will need to use the principle of RAG, which follows multiple steps that must be executed in sequence. Assume that you have a vector database available which contains relevant answers. Okay. So I need to user inputs a query, then I need to embed the query. Search the vector database using embed query and list of matches, augment the original query, and the return response from the LLM. This is the correct one. Then compare RAG with fine-tuning. When developing an application, you will need to incorporate company data and external knowledge. RAG and fine-tuning are both ways to achieve this. Understanding the unique features, benefits, and risks is vital for an effective application development. So, whether each statement aligns more with RAG or with time. Okay. Used for specializing in a new domain, this is fine-tuning. Requires labeled data. Fine-tuning, because if you want to retrain, extra components like vector database, this is in RAG. Then you will need, with this we will need to retrieve data. And this LLM retains original reasoning capabilities. This is with RAG, because with fine-tuning you modified some of the reasoning capabilities. Use it for including factual knowledge. This is in RAG too. Testing now.
We're at the final stage of development. Testing involves establishing robust processes to determine the readiness for the operational phase. Testing is crucial because LLMs make mistakes, especially as applications become more complex. Changes to one aspect of the application can affect others, impacting performance. Consequently, testing is vital for assessing the application's readiness for deployment. In this video, we'll specifically address evaluating the application's output. In traditional supervised machine learning, we use labeled training data and testing data to evaluate how well the model handles new, unseen data. We measure this using metrics that focus on accuracy or how close the predictions are to the target. In contrast, for LLM applications, you usually just need test data to make a test application. Here, the focus is on evaluating the quality of the model's output on this test data. A comprehensive test set is essential to effectively evaluate our application. Building the test set was a continuous activity during development, but should now be completed. The test data must closely resemble real-world scenarios to ensure accurate assessment. This can include either labeled text data for precise evaluation or unlabeled text data to simulate typical inputs. Various tools, including other LLMs, can help generate test data to facilitate this process. The second step is choosing the right metric. This depends on the application, but condensing it into a flowchart can guide us. If the model's output has a correct answer, such as a target label or number, use machine learning metrics like accuracy to assess correctness. We can use text comparison metrics when there's no correct answer, but we have a reference. The aim is to mimic how humans evaluate similarity and quality in text. We have two options. First, we can use statistical methods that compare the overlap between predicted and reference text. Second, we have model-based methods, where pre-trained models assess similarity. A popular approach is using LLM judges, LLMs designed to assess other LLMs, to gauge the similarity between the reference and predicted outputs. If there's no reference answer but we have human feedback, we can use feedback score metrics. One approach is to have humans rate the text on quality, relevance, or coherence, although this can be expensive. Alternatively, we can use model-based methods to predict expected ratings based on past feedback, or ask LLM judges if feedback was incorporated. Lastly, if there's no human feedback, we can use unsupervised metrics to assess text coherence, fluency, and diversity with statistical or model-based techniques. In addition to primary metrics, it's beneficial to keep track of optional secondary metrics. These can relate to text characteristics, such as bias, toxicity, and helpfulness. Alternatively, they can pertain to operational characteristics of the application, like latency, total incurred cost, and memory usage. This list is not exhaustive and is use case dependent. The combination of the test set and the evaluation metric determines when our LLM application is deployment ready. At this stage, tests can either pass or fail. If a test fails, we need to revisit previous activities covered. If it passes, we're ready for deployment, marking the transition to an operational phase. Let's test this knowledge.
Got it. Selecting an appropriate metric is crucial in evaluating the it's a text comparison. Okay, this is a text comparison metric. Okay, here. I think this here. Okay, wait. You are giving an example of a traditional machine learning metric or a text comparator metric is more suitable to evaluate it. So I need to check if, like, this application is better to check it with traditional machine learning metric or text comparison. Okay, and I'll ask her. It should be here, but for example, predicting the calories should be traditional machine learning. An LLM application summarizing chat histories, this text comparison. Is toxic or not? This traditional. Perfect. Okay, what answer best describe when you should be testing our application? What answers best describe when you should be testing? Regardless of the presence of a target output. Yeah. And then for the last one, let's take a small break because I need to check on my phone because I was supposed to receive a package. Okay, 1 second. So we are on 31 minutes. I guess that we'll finish now, and then I'm gonna come back